So we've already seen the triple integral in spherical coordinates, but we need to develop some intuition about where that volume differential comes from. So here we are looking at deriving the volume differential in spherical coordinates. Now, just like with the area differential with polar coordinates, this is not going to be a rigorous derivation, but it's going to provide us with some nice intuition about where the volume differential comes from and how it relates, again, to Riemann's limiting process. So as we begin here, let's keep in mind, what's our goal? What are we trying to show? So the goal is to show that the volume differential in spherical coordinates, dV, is equal to rho squared times sine of phi, d rho, d phi, d theta. So to do this, again, just like with polar coordinates, here we're going to start by considering a general spherical region. So below, I've drawn a general spherical region. We have the portion of a sphere in the first octant. Now, what we want to do to derive this differential is divide this spherical region into n spherical wedges, aka n almost cubes. So we'll keep that almost cubes in mind as we continue. So below, I've indicated one such spherical wedge. And so let's take this spherical wedge, this really, really small spherical wedge, and blow it up. So it's a really, really small spherical wedge, or almost cube. So if it's an almost cube, we need to think about the change in the length, the change in the height, and the change in the width. Now, because this is a spherical region, we're going to describe it slightly differently to start. So looking at our blown up spherical wedge here, we are going to see that we have a change in our height, or we can think about this as the change in going up. Now we can also see that there's this change in going around the sphere. So this is change in going around the sphere. And last but not least, we also need to consider this change in going out of our sphere. So what does this mean? The change in going up, the change in going out, the change in going around? We need to define this in a little bit more detail. How does this relate to those variables? So we'll start with the change in going up. So the change in going up. So the change in going up, if we look here back at our spherical region, that's going to be the change in the radius of the sphere. So this is the change in the sphere's radius. So in spherical coordinates, what have we defined as the sphere's radius? That's rho. So the change in the sphere's radius can thus be defined as delta rho. So we've got our first big change, the change in going up, or the change in rho. Now what about this change in going around? So again, looking back at our spherical region here, let's look at the biggest change in going around that's given to us. So the biggest change in going around would be this, going around the circle. So the change in going around this arc length. So this is going to be, think about what angle is associated with that arc length. Theta. So this is going to be the change in the arc length associated with theta, or involving theta. Now we know this arc length involving theta comes from polar coordinates. So thinking back to the derivation of the area differential in polar coordinates, we know that we can define this arc length, we'll say the arc length S, as the radius times theta. So what we have is the radius times the change in the angle theta. Now wait a second. R is not a spherical coordinate. That's a polar coordinate. So how can we change this? Well, let's keep in mind that since the radius r is defined by those spherical conversion formulas as rho sine of phi, we can rewrite this change in going around as rho sine of phi times the change in theta. So there it is. This is our second differential, or approximate differential, the change in going around. Now, last but not least, we need to think about what is this change in going out. So again, just like with the change in going around, let's look back up at our spherical region here. So the change in going out, we're thinking about going out along this circle, or this level curve. So this is the change in the arc length involving what angle? Phi. So this is the change in the arc length involving phi. So, and again, if you want to think about this in terms of your sphere, this little, really small spherical wedge here, this is that change in going out that we're thinking of. So the change in the arc length involving angle phi. So again, recalling the formula for the arc length, we can say that this is defined as the radius times the change in phi. So what radius is involved with phi? Rho. So this will be defined as rho times the change in phi. So we have these three changes. We have the change in going up, or the change in rho. We have the change in going around, or the change in the arc length involving theta. And now we have the change in going out. So that's the change in the arc length involving phi. But this is only for a really small spherical wedge. We need a sufficiently small spherical wedge. So how are we going to do this? Well, we need to again apply Riemann's limiting process. So here we go. It's our big finale. So we have that for a sufficiently small region. So in other words, as we let the number of subregions approach infinity, the volume of each subregion is approaching zero. So again, for a sufficiently small region, we can conclude that the volume of this really small spherical wedge is approximately equal to the volume of a cube. Woohoo! So in other words, we are saying that delta V, the change in our volume, is approximately equal to the volume of a cube, which we of course know is height times the length times the width. So thinking back to that really small spherical wedge, what's going to be the height, what is the length, and what's the width? So we can say that this is approximately equal to the height, which is going to be the change in the radius, rho. So that's the change in going up, multiplied by the change in the length. So that's going to be the change in theta's arc length, or the change in going around. And last but not least, this is multiplied by the width. So the width is going to be the change in phi's arc length, or the change in going out. So let's plug in those approximate differentials that we just derived. So the change in delta V is approximately equal to the change in the radius, or delta rho, multiplied by the change in theta's arc length, which we know is defined as rho sine of phi delta theta, multiplied by the change in phi's arc length, which we know is rho delta phi. So rearranging these terms a little bit, we see that delta V, the change in the volume of this really, really small spherical wedge, is approximately equal to, we have rho times rho, which gives us rho squared, multiplied by sine of phi, multiplied by delta rho, times delta phi, times delta theta, which looks awfully familiar. This is exactly what we were hoping for. Woohoo! So, again, as always, by applying Riemann's limiting process, by taking the limit of the sums of all of these n spherical regions, as the number of subregions approaches infinity and the volume of each subregion approaches 0, we can make the following conversions for triple integrals in spherical coordinates. So by Riemann's limiting process, we can say that the volume differential, dV, will be equal to rho squared sine of phi d rho d phi d theta. So the general triple integral, so we have that triple integral over that three-dimensional region D of a function in terms of x, y, and z, dV. And this, of course, is where, as previously mentioned, D is a three-dimensional region. This is your region of integration. And dV is our volume differential. Riemann's limiting process allows us to make the following conversions. So let's give ourselves plenty of room. So this is now going to be equal to the triple integral over that region of integration D of a function now in terms of spherical coordinates. So f of rho theta phi multiplied by that volume differential, rho squared sine of phi d rho d phi d theta. And now this, of course, is such that this region of integration D is now also in spherical coordinates. So D is the set of all ordered triplets, rho theta phi, such that rho is greater than or equal to rho sub 1, less than or equal to rho sub 2, that theta is greater than or equal to theta sub 1, less than or equal to theta sub 2, and that phi is greater than or equal to phi sub 1, less than or equal to phi sub 2. Now, don't forget that these spherical coordinates also have restrictions. This is where the radius rho must be greater than or equal to 0, where the angle theta must be greater than or equal to 0, less than or equal to 2 pi, and the angle phi must be greater than or equal to 0, less than or equal to pi. And so there you have it. We have the derivation, the intuitive derivation of our volume differential in spherical coordinates.